Welcome everyone. Thank you for joining us. I'm Cole Bush from BIOPAC. I'll be your moderator on today's webinar, a complete solution for eye tracking experiments in virtual reality. Today's presentation is super full, so I'll get right into the housekeeping so we can get started. All attendees are muted, so please submit your questions and comments through the GoToWebinar control panel. That's how you communicate with me, your moderator. We also have Sato Rabuti and Brenda Dettinger in the background helping to answer your questions. When the webcam is turned on, if it looks a little small to you, just drag that gray bar up and down. That'll resize it. Today's webinar is being recorded. We'll send each of you a link once the recording has finished processing. And finally, at the end of the webinar, we will have a survey. Please fill it out so we can have your feedback and ideas for future webinars. Now on to our presenter. I'm excited to introduce our expert today, Alex Dimov. Alex is the head of sales for Europe and has been teaching workshops on the topic of physiological data acquisition and analysis for over 15 years. While at UC Santa Barbara, he was an instructor for the Advanced Training Institute for Virtual Reality and Social Psychology. Welcome, Alex.
Welcome, everyone. Thanks.
Alex, I'm going to make you the presenter.
All righty. Let's just make sure we have the correct screen. Okay, very good. Okay, so I see some people are still coming in. Well, we will go ahead and get started anyway, since it's being recorded. So I think we're going to be fine. Thanks for joining us. Now, let me just close that window right here. Okay, so yeah, today we'll talk about eye tracking in virtual reality. So we'll present a complete solution for performing eye tracking work in virtual reality. Just a few words first. If you are not familiar with BIOPAC, we make equipment for measuring physiological signals and for stimulation virtually anywhere. So wireless, wired equipment, also in the MRI, etc. And our solutions are used by over 99% of the top universities in the world, both for education and research. And there are over 42,000 publications with BIOPAC. So what I'll be showing you today is a complete eye tracking system for virtual reality. Okay, so by complete, I mean it is a complete system that includes all the components you need to perform these experiments. So head-mounted display, rendering machine, software for generating the experiments, eye tracking analytics, the required bits to integrate with physiological data acquisition, with functional near infrared, with stimulation, etc. So what are some of the key points about this? So it's an out-of-the-box solution, and you can use it actually with no coding, or you can integrate into complex projects. There are eye tracking analytics, so you can find out which objects you've looked at, get data on that. We'll go into more details. It integrates with Acknowledge, which is our software for recording physiological data acquisition signals, so electrocardiogram, skin conductance, etc. It integrates with our functional near-infrared spectroscopy sensors, and it allows interaction with the objects in the environment. So not only are you there looking at things in 3D, but you can actually grab them, move them, walk around, etc. And you can also use 3D scenes and 360 videos and images alike. Sometimes you don't need to have a 3D scene from scratch. You can just use 360 images. So that's something you can do as well. And you can even use this as a substitute for a 2D presentation system, like on a computer with a remote eye tracker. You can do the same kind of things in VR. And very important also that the system supports multiple users. Now, we're going to do a technical demo right after our first ball.
Thanks so much, Alex. So yeah, if you're just joining us, feel free to answer the poll. What eye tracking equipment do you already use? And perfect. So as these answers are coming in, looks like about half of the people are using eye tracking bars or remote eye trackers, quarter using VR eye tracking, and then about a third are using glasses. So we will close that poll up and back to you, Alex. Let's get to the demo.
Okay. I'm showing my screen already. Okay, perfect. Oh, perfect. Okay, very good. All right, so this next part is going to be live with me putting on a head-mounted display, and sometimes our software for broadcasting this online confuses the screens. So Colt will let me know if that happens, so we can make adjustments. All right, so let's just jump straight into it. But I want to say a few things. First of all, I'll have the Acknowledge software running at the same time. So the virtual reality software will automatically start and stop the data acquisition. So when we start collecting the eye tracking data, we'll also start collecting the physiological data. And yeah, let's just go ahead and fire it up here. So, and by the way, we can run this also in desktop mode. This is very useful, and I'll show you afterwards running it in desktop mode, so you can try things out even when you don't have an HMD. But we have an HMD, so let's go ahead and do that. Okay, now here is this initial screen that you're faced with, and what I will choose here is to record our session. This will be very important because afterwards we can merge that video recording into our knowledge data. Okay, we can choose the fixation time. So when we look at an object, let's say you look at a cat, so if you look at the object for 1 second, it will be considered a fixation, or we could dial that down to 0.23 seconds. I'll leave it at 1 second so that everybody can follow along. So we'll keep the fixations a bit longer. And we're going to choose an environment. And I'll go into how we actually make this happen later. Now it's just a number of pre-configured environments. Okay, so I'm going to choose this environment. And inside each environment, there can be sub-objects, and I can choose which ones will be fixation targets. So I'm choosing the basketball and the soccer ball. And I can make some of these grabbable. As you can see, I've made the laptop grabbable. So using a controller like this, I can grab objects as well. But I won't be grabbing any objects right now, just showing you that this can be done. And then I'll visualize the gaze point so you can see what I'm looking at, and I'll make it extra large. Now the participant is not going to see this, or I will not see this gaze point, but you will, so you can know what I'm looking at. Okay, and now let's enter some information here. So this is the participant information, and let's come up with some random number here for our experiment. And yeah, let's get Acknowledge onto the other side so you can see how Acknowledge acquiring data at the same time. And then we begin. So I'm going to put on the head-mounted display. Okay, and well, I'm not sure. Let me just make sure that I've enabled the. Okay, so you should be seeing now my gaze point. So I'll look at this creature right here, and it's going to smile at me because I looked at it. I'm going to look at it again. It's going to smile at me again. Now these chickens, they'll react to my gaze as well. So they're quite happy that I'm looking at them, they're jumping up and down. We can look around in the room. We have all sorts of objects here. So here we have a soccer ball. We'll fixate on it. We have a basketball. Look at the soccer ball as well. And then we'll look at the chicken right above it. that's sufficient for our purposes. So I'm just going to get out of it right now. I'll press space bar so it stops the recording, and it also stops acknowledge. Okay, now one thing that happens right away is you get this report generated. So we have a number of objects here in the room. We have little chickens, we have the creature, and basketball and soccer ball. So we can look at some basic analytical information. So total view time and average fixation time. We can see we never looked at two of the chickens, which is why they never moved. So this is also generated as a PDF. So right now I'm just going to close it. Okay, we no longer need this, but you can see that we also have the points, our gaze path. Okay, so now let's just go ahead and look at the software and acknowledge. So okay, let's auto scale the data. Now you can see all these markers were coming in. So we looked at the creature, we looked at the creature again, the chick, soccer ball, etc. So all of these are markers that came in over the network from the virtual reality component of the system, from the Wizard software. Okay, so now something else we can do is we can link up media. So we'll come over here and we're going to look for the file that was generated. So that's the one. Okay. And so I'm going to place it like somewhere here. Actually, let's have these side by side like that. Okay, there we go. And here are our events. So now here we are looking at the creature. I can make this a little bit bigger so you can see it better. So here we're looking at the creature. We can play it back so we can see we looked at it and it smiles. And then I looked at it again and then it smiles again. So the video is linked with the physiological data. You can click on like the soccer ball, for example. You can see the soccer ball right here. I'm looking at the soccer ball. So that's very useful. Everything's linked together. Now, since we got all this information in real time about when we looked at the various objects, and here we can see the descriptors, we can perform some analysis and acknowledge. So here we have some ECG, and by the way, I'm not connected right now. There's just too many things going on right now to be connected. I use acknowledge in playback mode, which is extremely useful for when you're testing, when you're preparing an experiment. You can actually play back data and make it look like the real thing. All right, so we'll go to analysis, find rate, and we're gonna base this off the ECG. So this is just heart rate from ECG, human resting heart rate. Let's give it a bit more of a tolerance. Okay, and now we're gonna end up with a new waveform here on the bottom, which is the heart rate. Okay, so let's hide the other one. So here's our heart rate. And I can very quickly generate some useful analysis. So I can say, let's do a stimulation response analysis. At each stimulus event, I want to grab the next 3 seconds. And this will differ depending on what you're doing. Is it electrodermal activity, heart rate, etc. So a bit arbitrary right now, just showing you how it works. So at each stimulus event, I'm going to get the mean. Actually, I want to get the rate mean of the heart rate channel. And yeah, let's just go ahead and get this into an Excel spreadsheet. So now we have here for the creature, we can see 2 times that we looked at it 2 times, and now we have the heart rate. Then we have for the chicken, we have it for the soccer ball, etc. So this could be a number of different physiological parameters that you're requiring. And since you have the data for fixations, then you can perform this analysis. Now, something else I want to show you is there's also automatically this data folder that gets updated. So this is the PDF, okay, the PDF that I showed you initially. Okay, so that's there. Now, in addition to that, we have the tracking data. So the tracking data, it shows us XYZ and also gives us the pupil diameter. Okay, and when relevant, it also provides information on, there we go here, on when we have looked at a new fixation. So this, for example, this pupil diameter information, this is just the text format. So we can bring that right into Acknowledge, and it can become another channel in Acknowledge. Okay. Something else that we can do is now we can come back to the virtual reality software to Wizard, and we can replay our session. So let's just hit here. Okay, and we're going to use the desktop, but we could view it inside a head-mounted display, but I'll use desktop mode. Let's click OK. And our participant ID, as you can see, I've been very creative here with my numbering of participants. Is 3333. So here we are looking at the same scene. And if we click to static, we can see our entire gaze path, you know, for the whole experiment. You know, if I move here, you can inspect things a little bit closer. Okay, now I can go to dynamic. And if I go to dynamic, it's actually going to play back what happened during the experiment. So let's just press spacebar, so visualizing it. Okay, so this is my avatar looking at stuff. So okay, looking at this creature, looking at the creature again. Okay, looking at the other chicken and so forth. Okay, let's pause that. So a lot of different things you can configure here, and the pupil diameter is shown right here. So it's also provided here. All right, well, let's escape out of this. Okay, now that's what I want to show you right now, and we'll continue with more examples after our next pause.
Thank you so much, Alex. Excuse me. We actually do have a couple questions coming in. Once again, if you do have a question, just type it in on the questions tab through the GoToWebinar, and either myself, Brenda, or Sato will happily answer. One of the questions to you, Alex, is from Tom. He asked, how long did it take to put together that virtual space?
That is something that I will show right afterwards. That's actually incidentally the next part of my presentation. I'll show you how that's made.
Perfect. Well, there we go. As far as the poll, what is your comfort level with programming? Looks about half are saying they're comfortable with doing some programming, and then almost 40% saying minimal programming requirements are okay. So we'll push it back to you, Alex.
Okay, thanks. All right, so hopefully everybody can see my screen now. Now, I'm going to answer a few questions. So where did these three models come from? How do we create this experiment? And how do we make it interactive? Okay. You know, there's actually a lot of choice these days for getting 3D models. And I just bought the 3D models. And there's also a lot of free ones on Sketchfab. So Sketchfab has a tremendous number of 3D models out there. So here's the creature. So if we look at the creature here. Okay, so that's the creature that we used in the program. So yeah, it has a number of different animations. And I just downloaded the GLTF format. That's the format you want to make it work with Wizard. So you need the GOTF format. So in fact, all of these things are just without any additional work. Just get them from the web, like the room here. That's also just a 3D model. So I did not actually create any 3D models. I just got the 3D models. And I placed them in a folder called, let's go to our resources. So this is basically the structure of the site lab. That's the eye tracking analytics lab. So you have this folder called resources, and there we have environments. Okay, so now here is the environment. Okay, so that's just that model downloaded, and then you see the format's a bit different. It's OSGB. So what I do is when I open it up, I just save it as OSGB, just because that's the native format for using it in the experiment. So and you can do things like resize objects, rename them, etc. But I'll show you what I did do. So if you click here on one of the objects, for instance, here we have the basketball. Okay, initially it wasn't called basketball, so there was no way for, we had to tell the program somehow that this is an object that should be tracked in the program. So for instance, okay, here we have an object. Okay, here we have a bunch of these objects. Let's just see what else we can find. Okay, so here we have the TV. Okay, so that's the TV object. So to make this an object that is used in the eye tracking, we can just come over here and say insert above and make it a group, and then we rename it, and we just call it TV. All right, so that's all we have to do, and then I'm just going to save. I'm going to save this just over the old model. So now there's an object here called TV. So with this information, it will now be in the list of objects that can be tracked. So let's just verify that. So we'll come back over here, and we have the main program here for the 3D scenes. So just execute it again. This time I'll use it in desktop mode. Okay, so we're not going to record anything. I just want to click here on configure, and now you see we have a TV, and we can make it a fixation region or not. So that's basically how easy it is, at least for those objects. Okay, but I did add these additional objects that I was able to interact with. So that's where you have two levels of expertise here. So if you don't want to, or you can't program, you can just get a 3D model, and you can name parts of it, and they will become accessible. So you can set these as up as targets to track. You can even add additional objects. So see, there's a bunch of objects already included, but you can download more from the internet. Like I'll just add a chair. So here's a chair. Okay, now this chair will also become an object that can be tracked. Okay, so here's our chair, and we can do things to the chair. So we can move it around. So in the world, we can reposition it. We can change its size. Maybe we want it to be really small and see how people react. Okay, so and you just place these objects into the objects folder. Okay, so you can make your own or download from the internet. The reality is everybody's just downloading things from the internet these days, because let's just have a look here. Let's look for chair and downloadable models of chairs. So there's so many chairs. A bunch of them are free, some of them are paid, but there's a lot of objects out there that you can just use. Things have changed in years past, that's for sure. Okay, so now let's go and look at how do we make something more complicated. That's adding interactivity. So now we're gonna go down into the code, and like right here is where I edit the objects that have interactivity. So I have a bunch of chickens, And all I've done is, add the chicken and place it in a specific position. But how do I know where, right? How do I know where to place the chicken? That's very easy. I can come over here into my scene, and if I want a chicken like to be placed like right on the chair here, for example, I just point there, right click, copy 3D position, and then I come back over here, and you see it just pastes the 3D position. So I could just replace these coordinates, and I can place the chicken there. So I come up with my arbitrary names for my chickens, and then I have the creature. And then notice that the creature, I've done a couple more things to it. I've set its orientation. That's just make it turn 22 degrees to face me. And then I changed its state. Okay, let's look at our creature here. So let's go into the objects. And here is our creature. Okay, so the creature, that's just how it came. When I downloaded it, it has these various states, animation states. So now it's idling, it's waiting for me to look at it, and there's different kind of smiles. So okay, so now it's smiling and so forth. So these are just different states, number 5, number 6. Okay, the chickens are the same way. They come with animations, they're animated models. So now, how do we make it interactive? Well, here we have these functions that are just part of the system. So you go on gaze time, and that means when you've made a fixation, I'm adding a couple of extra things. So first of all, I'm adding this line here. That's the line that tells the software, let's send a marker to acknowledge, and it's going to have the name of the stimulus, and it's going to be a stimulus marker. So this is the single line. It's all we need this is all documented in the documentation, right? To get the marker in acknowledge. So these markers right here that say creature, chick 1, chick 2, that's how they came in. And the interactivity, here I say, okay, if the object is the creature, let's change its animation to number 6, which is the smiling animation. So I look at it, it's going to smile. And if it's the chicken, it's going to jump. So that's its animation, number 10. And in that tool here, which is called the inspector, you can very easily check all these things, like look at your avatars and look at the objects. And then I say, okay, well, when the gaze ends, what happens then? On gaze end, so once I'm no longer looking at the objects, I change their animation. So the chickens are now idling, and so is the creature. Okay, and so basically that's how it works. So you can just use it as is. You can get 3D models and just perform an eye tracking experiment. But if you want to interact with the environment, you can get into the code and you can start making changes. And because the functions are, nicely named, and there is also extensive documentation that tells you exactly what to do, it's really not that difficult. Yeah, let's take a break now, and we'll continue with some more examples.
Thank you, Alex. We do have some questions coming in the questions panel. We have a few from Carla. She asks, what happens if there is noise when you're collecting heart rate because the participant is moving while in the virtual reality space?
Yeah, well, first of all, when you are recording heart rate, if you're using electrocardiogram and you have using good proper practices to clean up the sites first, make good contact, place in lead to configuration, etc., you can get to a point where you just don't have noise. So that should be the primary goal. Okay. Now then we have wireless and wired sensors. So depending on your paradigm, one or the other may be more appropriate to eliminate any the potential problems caused by movement. So if if you're wired, you can only go so far. Now let's say that you mess something up and you don't get good data. There are still techniques you can use to deal with that. And we have in other webinars we've covered that. So it may be good to afterwards add an answer to that question, maybe to our FAQ, where we direct to resources for what to do when you did end up with noisier data. There's two techniques, but the main objective is not to get noisy data in the first place, because you can get it very clean.
Yeah, well, thank you, Alex. And as far as the poll results go, looks like most people will be interested in EEG, ECG, and EDA. Back to you.
Okay, thanks. Okay, now I want to show you something else, another analysis tool that's part of the eye tracking analytics. It's a heat map. So here we have the room, and I'm just going to play back the recording that would be generated after looking at the room. I don't have any of the creatures in here for simplicity's sake, so let's just play this back. So now this is a replay of what the participant has done. So we're just looking at the heat map. Now, I want to point something out, because you're all viewing this right now remotely. You're probably getting a very jittery view, but keep in mind that the head-mounted display is actually updating at extremely fast rate, so everything is extremely smooth, and the experience is completely different from what people would see during a webinar. So that's just something to keep in mind, because what you see on the screen is limited to the bandwidth, and it's going to be very jittery, but in reality, everything is extremely immersive and smooth. Now, I want to show another example here. And just say a few words first of all. Now, traditionally, when you're doing experiments with eye tracking, and maybe you're presenting something in front of a computer for 2D images, we can really evolve this a step further in virtual reality. Like, you can walk around, physically walk around, or move around in a gallery where you have images, for example. And then it's more subject to the participant how to interact. Of course, you can impose the same kind of tight controls that you would in front of a computer, but you really can think outside of the box here. So let's just look at an example where I will put on an HMD again, and I'll be inside of a gallery, and now I'm going to have fixation regions. So when I'm looking at parts of that space, instead of objects, this time there will be regions of the space that will be subject to eye tracking analytics. So let me just open up here this, and this is another 3D model that this one is a free 3D model that MTV put up on Sketchfab. So just fire it up. Oh yeah. I really don't want to make those changes to my original document here. So yeah, let's ignore those changes. Okay, so I'm going to use again the Omnicept, HP Omnicept. Okay. And this time I'm not going to record the session. You've already seen how that works. I'm just going to go in it. And so, no recording of the session, but now it's a different model. This time I'm going to choose the MTV gallery. As you can see, inside the gallery, we have a bunch of objects that are defined. So you see what that means. And I'm not even going to fill this out because I'm not collecting the data. So let's just begin. Okay, so here I am now in the world. so I'm looking around, and so now I can look at different parts of the world, and there's different there's different objects in here. Okay, and I can also move around in the world, but I forgot to turn on my controller, so that doesn't help me much. So let me just do this the right way, so so you can see a little bit better how that works. Let's just, okay, now controller's on now. Okay, so let's stick to this. Okay, everything's configured the same way. So I grab my controller here. Now, what I can do here is I can also turn around. I can navigate this world, just go to a different place, look at the artwork. So come over here. And I've set these up as tracking areas. So I can actually track them. So even though they're not 3D objects, come back over here. Okay. And I can turn around here. So this way of navigation is pretty easy. I don't even have to walk around. The participant can do it while they're just sitting in a chair, and they will not get sick because it's just rotations and teleportations. So yeah, let's stop here, and now let's have a look. We have some data for where we've looked. So we have our areas of interest, right? So Ariana, Brittany, Nick Jonas, Rihanna, so we can see how long I've looked at each of them, you know, average fixation time, etc. Let's escape out of this. Now, the reason why I'm showing you this, it's a little bit different than the other 3D scene. Now, we did not add additional objects to look at, but instead we define regions inside. So how do we do that? So let's go here to our model once again. So we'll go into the resources and environment, and so this is the environment. Okay, so we're gonna go inside environment. Okay, now let's look at one of the objects here. So for instance, okay, one of the things I wanted to track was this. Okay, so how did I do that? Well, I've added these objects, like right here we have an object, but it's transparent. It's an object that is right there, and then if we turn around here, so here is the Brittany one, and there is another object. Okay, it's like right here is the object you can see, but it's transparent. Actually, we can make it not transparent by changing its alpha. This makes it easy to reposition the object. So I can move it to a different place. Okay, and that object is originally inserted by just going to add, and then you go to the default objects, and there is fixation region, and fixation region is just this object here, and then you can resize it, move it around. So basically all I'm doing is, yeah, let's just import this object and place it in a new location. So I can now just say, you know, let's copy this and come back to the top of the scene, and so yeah, just come over here, copy, paste, copy. Okay, and now we have two Britneys. So I will go ahead and rename this, and I'll call this test. Okay, so you can see here, it's like right here is that object called test. You can also see it from the other side, and I can move it. I can just say, you know, let's just move it over here, and now it's going to represent that region here. Okay, and right now these objects are not transparent. You can make it transparent again by just coming a level down and changing the alpha back to 0. Okay, but I will not do it right now. I will leave them like this so you can see how they look in, if you want to just test things out. You want to see where your fixation regions are when you're exploring the environment. So I'll save this, I'll call it test, okay? And now I'll just go back in here, but now I will load the test model instead. So yeah, let's ignore that. Okay, desktop mode this time, okay? And this time we're going to test, okay, very good. Test 1. Okay, now I'm using desktop mode. You can see they're green. They're not transparent because they don't make them transparent. And now the fixation region reads out test. Here it's Brittany, and here it's test. So desktop mode is very useful. Okay, and we end up getting our analytics in the end. Okay, I'm going to close this so that I stop getting these warnings. Okay, now so this is what I wanted to show here, is how to create these fixation regions. And I also want to show you now how to work with 360 images and videos, because of course anybody can now create a 360 image or 360 video. So it's become much easier. And yeah, how do you run an experiment with it? So I've downloaded a free one off the web again. So if we come over to resources, media, I've downloaded an image here. So that's just a 360 image, okay? And I've placed it in the folder, media. So we come back here to this other example, which is how to deal with the 360 media. I'm only going to use right now the desktop mode. I think that's I don't have to put on the HMD anymore for you to get the idea that it works with an HMD. So desktop mode, and again, we can do a recording, and we have to say, is it a video or is it an image? Is it mono or is it stereo? And we choose what it is. Okay, and so let's continue. And here we would put in our subject information, but I will not do it right now. So here is the scene, and if we look at the house, you can see it says gaze fixed on the house. Okay, and then gaze fixed on the peak. And now we have gaze fixed on the grass. So how did it know? And here's our gaze path at the end. So how did the software know what I'm looking at? Okay, so the way you do that is you do an initial run where you do generate a recording. In fact, I already did that just before starting the webinar. So if we go up here into recordings, you'll see a recording here that I already did. So now there are no areas of interest, but the reason why I did the recording is that now I can know at exactly what time I'm looking at the house, and then at exactly what time I'm looking at the peak, okay? And then if we look at the data, and the data now is right here, so it's the tracking data. Okay, so if we come over here, I'm looking at the Machu Picchu peak here, 9.35 seconds. So then I can scroll down, get to that point where it's 9.35 seconds, like right here, and I can get the coordinates of that. Okay, and then in the code itself, there is a place where you can define fixation targets. So this is an example where you have to do a little bit of coding, but it is again just using an example that exists. So So here we have our fixation areas. So you can see right here, these are tracking coordinates. So a little bit different because I took a point in time that was a little bit later. So anyway, we just, what we do is we define a fixation region, and it's going to be a sphere in this case, but it could be other shapes. You know, it could be a cube, doesn't have to be a sphere, it could be a different kind of shape. We make it transparent so that we don't see that region, but you can make it non-transparent for testing purposes. Okay, so that's if you want to test it out. So we just use that sample code, and then this fixation areas 1, 2, and 3 are respectively house, peak, and the grass patch. And we just put names of our own here. So these are, again, there's very clear instructions. So if we look into the documentation, these are the documentation. So you can see here. So if we just look for 360, okay, so fixation areas for 360 images and videos, there are instructions you can just follow. And it's the same with all the other things that I showed you. It's all described in the manual, pretty straightforward what you have to do. With video, the only difference is that in addition to coordinates, you also define the time. So when does it appear? When does it go away? For example, if it's moving, you can define the path where it's moving. So you can really track any fixation areas, objects, etc. That you may have in your experiment. Okay, so next we're gonna have a quick poll and go into the final part, which will be about adding all these physiological signals that you can.
Thank you, Alex. Again, we have a bunch of questions pouring in. Sato and Brenda are doing great jobs of trying to answer everything. One for you though, Alex, is Anna. She's asking if you can integrate an audio file into the system.
Yes. I mean, really, of course, yes. So this is it's a full-blown VR toolkit, right? So you can really do anything. These are just specific tools that augment the capabilities of what you're able to do in VR. So you have a graphic user interface, or you do it with changes to the code. But other than that, it remains a full-blown VR engine and a VR toolkit. So you can do that and anything else. You can interface with all sorts of devices like gloves, etc. Right? Yeah.
Perfect. And as far as the poll is concerned, a little more than half have participants interacting with their environments, and then a little more than half also create their own, and they're interested in biofeedback type of experiments. Back to you.
All right. Thank you, Colt. So what about adding physiological measurements? We already did a demonstration for what it would look like if you had our MP160 system connected. So with our MP160 system, you can connect many different physiological signals. I'm going to concentrate on a few common ones that come up in the context of VR. So let's look at stress, for example. So we can record heart rate variability using electrocardiogram, as well as pulse measurements. So if you can see here, these are our wired sensors. They're just really like very, very small amplifiers. You know, the wireless ones are just little devices that you can wear like this. So you can have sensors like wireless or wired for heart rate, pulse, electrothermal activity. We have a blood pressure sensor that's, of course, it's wired. You can do cardiac output, pre-ejection period, total peripheral resistance, respiration, all these different stress-related measurements and related to many other psychological function as well. So in addition to that, you can record functional near infrared. You can see here our functional near infrared system used under, and I'm just going to grab a sensor here so you can see. Then you can see like this is a sensor functional for the functional near infrared systems. It's very thin, and as you can see, it fits under the head-mounted display under this one right here, for example, the HP Omnicept. So what is functional near infrared? I'm pretty much going to assume that some people know, but some people don't have any idea. I'll try to be brief. Functional near infrared is used to measure changes in oxygenation in the brain. They're correlates of brain activity related to oxygen consumption by neurons. So we shine infrared light into the head, and we're looking at how much light comes back. And then oxygenated and deoxygenated hemoglobin, they absorb different parts of the infrared spectrum. So by looking at what light comes back, we can know if there was more or less activity in the brain. So since we're going to share these slides with you at the end, I've put in some information you can review afterwards. This is what the sensor looks like when you slow down greatly, the speed at which it operates. It's illuminating the brain. So you can measure from the left medial and right prefrontal cortex. Keep in mind that when you are using eye tracking, you only are able to measure from up here. So over here, eye tracking systems put out some light that interferes with the bottom sensors on the sensor. So you're really using about half of the sensor. The other part will get eye tracking interference, but you will get half of the prefrontal cortex just fine. These are sort of the regions you're getting data from. Now, and functional near infrared is measured is used, for example, for measuring cognitive workload. And we have tight integration with the system, so we can actually stream in real time the data, the oxygenation data, into the virtual world, and you can use that for biofeedback if you want. So you can see here how it's streaming the data back into the world, and then also we can send markers just like we can to acknowledge. We can send them to the functional near infrared system, so it knows when I looked at the chicken, when I looked at the creature, at the soccer ball, etc. All these things are going to can happen for you automatically. The different kinds of systems that we have. So there is one system that you can wear on your arm, and then it's wireless. Then you have a wired system, and then you have like a big wired system for connecting multiple participants. And you can connect multiple participants with all these anyway. And they can also be multiple participants in VR. Now, EEG and cognitive states, that's also, we see a lot of people interested in that. So this is a wireless system, 9 or 20 channel wireless system that fits, again, very comfortably under the head-mounted display. You can see here a picture. And then you can measure cognitive states like engagement, confusion, distraction, drowsiness, workload, and stress upon completing an initial calibration. So there's an initial calibration that you have to complete, like a cognitive task, and then you can measure these cognitive states during the experiment. Once again, to make it clear, we have this full integration between the physiological data acquisition and the virtual reality component. So we can stream physiological data into the virtual world. So here is an example of it. On the left side, we can see, and yeah, let me turn down the volume here. So on the left side, we can see the virtual reality display changing, and that's as a function of the data in acknowledge. So that's respiration data. So when we're inspiring, it becomes blue. When we expire, it becomes red. When we inspire again, it becomes blue and becomes red. And then the balloon moves up and down. Very rudimentary. It's just to give you an idea of how it works and that it does work, but you can extend to all sorts of biofeedback. Stimulation delivery. We have a send delivery system that can be controlled by the virtual reality software, and that's very useful. Like imagine you're looking at a pizza, the moment you look at it, a smell is delivered that corresponds to that. And so depending on how you're interacting with the stimuli, we can change the delivery of scents. We also have electrical stimulation, thermal stimulation. For example, this is the thermal stimulator. And imagine looking at a cold object and then feeling colder temperature on your hand, and then looking at something hot, and then you're getting different kind of feedback. So many options exist because of the high level of integration that we have achieved between all these different components. Well, we are now at the stage where we're ready to take more of your questions.
Yeah, wonderful information, Alex. Thank you so much for taking the time to explain all that. I know it's a lot, so it's thank you again. That was amazing and very cool to see. We do have a lot of questions coming in, and Sato, feel free to join us as well. Our first one, you kind of touched on it a little bit. Alex, does the HMD produce any artifacts when collecting EEG signals?
For EEG, no, not really. It's the main area where you will get artifacts, and that's in the optodes right here, the lower optodes. That's for functional near infrared, and so you just use the optodes, the second row of optodes.
Perfect. Our next question comes from Daniel. He asks about the complete solution part. He says, does this include the HP Omnicept used in the demo? What does the complete solution include?
Yeah, so it includes everything you need to perform the experiment. So it includes the rendering station, the software for creating the virtual reality environments. It includes the eye tracking analytics. It includes the integration with Acknowledge, integration with FNIRS, examples, support, etc. So you just get a system that works, right? So you want to do virtual reality experiments with eye tracking, even if it's without eye tracking. So it's just a complete system. So that's really one thing we've seen. There's so many options to configure. It can be really rather complicated to reinvent the wheel. So the idea is that you just end up with something that is going to work, and it's designed for researchers. It's not a game engine. It's based on Wizard, so it's Python based, and it's very well supported.
Yeah, definitely. Thomas asks, do you have your own eye tracking calibration method, or do you use manufacturer's method? He's just asking for best eye tracking accuracy.
Well, the eye tracking, there's already eye tracking calibration tool that comes with the headset. So I don't know if Sato wants to add anything to that, but
yeah, I mean, it depends on the SDK from the headset itself. So HP Omnicept, for instance, has a built-in calibration method. Some of the other headsets, we have our own calibration method, just depending on how that's kind of like set up in their SDK. But for the HP Omnicept, that's their proprietary calibration that you run through their software.
Okay. Mark asks, can it work with interactive virtual reality games and educational tools?
So the idea is that you would create these, right? So since you have the software to create them, and we have another webinar that I did last year, or maybe it was the year before last year, on how to create a stimulus paradigm in VR, which is kind of like a game, right? So you can create these worlds, these experiences with the software, with the Wizard software. And it's really designed so that researchers can do it without having to be super experienced. Okay, So, and for education as well, you can use this, of course, for education. How exactly, that's a separate discussion to have, and we would be very interested to separately discuss with you as well.
Okay, another question coming in. How robust is the eye gaze tracking, and what is the frame rate for the tracking?
Sorry,
Uh, how robust is the
oh,
eye gaze tracking, and then what's the frame rate for the tracking as well?
yeah, say what is the HP Omnicept frame rate for tracking? Do you know?
I'm not sure offhand. I mean, I think it's like most of them are somewhere around like 120 to 200 hertz. I guess I'd have to look up what the Omnicept is. I mean, as far as measuring the accuracy, that kind of depends on making sure that you calibrate each time when you have a new participant. And so then it checks that your IPD, like interpupillary distance, is correct and all that's set up and the headset's on correctly, because if there's a loose fitting headset, that can affect it. There is a way to run sort of a test where you can look at an array of balls and see that it's tracking accurately. And with the Omnicept, you can also get a gaze confidence level that it'll show as well.
Yeah, and you also see when you look at objects, when you test it out, you know how accurate it is. As Sado said, you can look at targets to also verify what is really going on here. And yeah, subjectively, I can say this looks pretty, the experience is pretty good for tracking.
Yeah, and also as far as frame rate, I mean, if you're looking at a 3D scene, then that would be just the frame rate of the headset. That's and I think I don't know what the Omnicept is actually offhand, but usually those are between 90 to 120 hertz.
Yeah, that's kind of more of your limiting factor, but yeah, exactly.
Awesome. Another question asked, is there any integration for a smartphone or a pointing device within this system?
Well, I'm not sure exactly. Well, so it's a separate thing, right? So if you want to be performing eye tracking experiments on a smartphone, we do have scene camera glasses for that. So you can wear the scene camera glasses and you can perform mapping of the screen, so you can track it. So you can actually put markers on the phone, so then you can track exactly what you're looking at the screen. So that would be a real world experiment, right? But you could do the same one in VR. Like you could use your controller to work with a phone. You can use a data glove. This is really like sky's the limit for what you want to do. But I think based on the question, maybe more of a question about real world smartphone experiments.
Yeah,
But it can be.
and this also could be diving a little deeper into just the possibilities of what you could do with the underlying program. We do have people that have used a phone or a tablet, for instance, to control a VR experiment. So you can be able to then connect to like a browser basically, and you can control things in the VR scene with the phone. If that's, I don't know if that's related, but that's just a little deeper diving into doing something with the software.
Yeah.
All
Yeah,
right.
and
And
then
then, oh, go
if
ahead,
we
Alex, sorry.
another offshoot of that, like going a bit deeper, right? Since there's also a position tracking system, infrared position tracking system that can be used. That we use for VR, and that gives you sub-millimeter precision. So you could also be tracking an object that you're holding and how you're interacting with it. So there's really like a lot of options.
No, you're right. I mean, this stuff is so cool and I love it. Our last question before moving on. You actually answered this in the chat, Sato, but just to say again, because I thought it was super important. Which VR headsets are compatible with the system?
Yeah, and so that's what Alex was showing us, the HP Omnicept. That's the newest eye-tracked headset that we've integrated with, but also the Vive Pro Eye is a very popular one, and that works. And any of the Tobii enabled VR headsets, so there's some older ones like the Tobii original Vive headset, as well as Pupil Labs, which is a device that you can pop into existing headsets that just has a little eye tracker that you can pop into like a Vive or an older Oculus. It also will work with headsets that don't have eye tracking built in, but then you'll just be getting head position and not eye tracking. But if you're using like a Quest 2, for instance, then you'll still get like your attention, but it'll be obviously not using eye tracking, but that will work with the software. It'll just get head position.
Yeah, just to add to that, that's actually very convenient. For example, at home, I don't have this headset, but I have a Quest and have a regular Rift. These are just don't have any eye tracking. But if you're doing some sort of interactive experiment, or it's still very, very good. You can design your experiment even without actually using the eye tracking, the more expensive eye tracking HMD. So you know, that's very convenient from a development standpoint, and that desktop mode should not be underestimated for that either, right? The desktop mode is very useful for development.
Great. Again, thank you guys so much, for answering the questions. For those of you listening, we'll also be putting together all the questions into a Q&A document and be sending that out in the next few weeks here. And yeah, like Alex said during his presentation, we do have live and on-demand webinars. Our next webinar is February 10th. We're very excited. It's the data acquisition fundamentals. Just going to go over how the MP160 system works, from setup to plugging in amplifiers to everything in between. That one's hosted by Tim Cook. He's great. And like Alex mentioned earlier, if you have any questions on ECG, Acknowledge, EDA, we have a ton of webinars on our website. All you got to do is go to the biopac.com/webinars page. I'm going to drag it over here. And like I said, you have everything from best practice for good data to education to eye tracking webinars, VR webinars, everything that BIOPAC does. And last but not least, today's webinar was recorded. We're going to email you guys a link of today's recording. We'll also email you the slides and the question and answer document as soon as we have that. When you guys close the webinar, you will see a survey. Please complete it so we can have your feedback. We always take your ideas for future webinars. And feel free to visit biopac.com for any additional references. Might be screencasts on specific features and analysis tools, application notes providing step-by-step instructions. Like I said before, information about upcoming webinars or past webinars and anything like that. Before we conclude, Alex and Sato, do you have anything else you'd like to say?
Just one comment. We are, of course, very interested in hearing how you might want to use something like that, and maybe ideas you have for adding functionality. It's obviously ongoing project as people come up with all sorts of things. So.
Yeah, I would second that. I mean, any additional comments or features, yeah, feel free to let us know. And yeah, thanks to everybody for participating and joining. And thanks to Alex, yeah, putting this together.
Perfect. Well, yeah, thank you, Alex. Thank you, Sato. Thank you, Brenda, for all helping out. Thank you to everyone for attending. This is going to conclude our webinar. Thank you again, everyone, and we will see you next time. Bye-bye.
Bye.